So today I have a big pleasure to introduce Adrian Muntean from University of Karlstad from Sweden. And let me just give some little introduction. So he did his master thesis in Napolka in Romania. Then he received in 2006 in Bremen University his doctoral nature in Germany. Then he was working in a Center for Industrial Mathematics during period 2001-2007. He continued as assistant professor in applied analysis in Eindhoven in Netherlands. And finally, he became full professor in Karlstad University in 2015. And today he will speak about very interesting subject. What is it? Does vesicle microdynamics and enhancement the signalizing among plants macro transport? Okay, so we are looking forward of your talk.
Thank you, Sharka. Thank you, Martin, for the nice invitation. It's a pleasure to be with you here in Prague or online. It's also an honor to give a talk in the Necas seminar. This is for me for the first time. Of course, I knew about it, and now I try to follow some of the talks, as Martin kindly put me on the followers list. I take this opportunity to speak about a math biology problem. It's not math biology is not really my field of research. This is, in fact, one of the first moments I'm speaking about a math biology problem, but I'm using it as a motive for a multi-scale discussion, which is in fact the core of my talk. Since I most likely will not be able to control my time, Sharka, Martin, please let me know like 5 or 10 minutes before the talk is. You expect me to finish the talk to come to a conclusion. Okay. Okay. So let me enter the discussion. So this is what I plan to do today. In one slide, I would like to present briefly my group in Karlstad, and then I would like to show you some preliminary results I have on a multi-scale problem coming from biology, which I think offers many new problems to work on. And in fact, I'm using this opportunity to search for collaborations, should some of you be interested into that. So, okay, so let me tell you a bit the group. So I work with 3 PhD students now, and I have a research assistant. Vishnu is working on homogenization and emission reduction for reaction diffusion systems, which is in fact my core expertise. Omar is more a numerics person. He works on multi-scale models, stochastic and deterministics for heterogeneous media. And with Surendra, we started to look into diffusion of some species into hyperelastic materials like rubber. While with Emtinan, I'm trying to understand what all these people around me start to work on data science, data classification, and things like that. We are just learning some of the issues. Okay, concerning the topic of today, it's a joint work with Sander Hiele from the Mathematical Institute in Leiden, who is who has expertise especially on semi-grouped measures, and with my PhD student Omar Richardson here in Karlstad, who in fact he's an expert in reactive flow in porous media. And the kind of work I'm presenting here is supported by the so-called Magnusson's Fund of the Swedish Academy of Science. The results I'm presenting here are new, but they are relying on some older results of mine, and especially with Sander, which I will tell you a bit as time comes. Now, what is about? In fact, the problem comes from Leiden, from the environment of Sander Hiele, from the biologists there. They would like to understand transport of nutrients in plants. So they just want to grow in a smart way, in a controlled way, plants. Now I show you here some, I'm interested in microstructure. So these are plant microstructures I'm showing you here. In fact, there are pollen microspores. I'm not 100% sure you can see the picture. Can you properly see it? Do you see this flagella, this kind of, do you see the picture properly?
I think we see, at least I see, I have a feeling that I see the picture.
Okay,
properly.
okay. That's enough. It's, I mean, more than that, I cannot see myself neither. So, you could see some rounded little balls like this. They might be slightly moving or fixed in space, but they're typically moving. These are actually these biologists. They grow pollen in some sort of petri dish. So you see these microspores. So what happens with this? What do they want? These biologists, they want to how to say, each of these microspores has many tasks in a plant tissue. They ultimately want to grow, or they want to have some kind of sort of sexual behavior. So in fact, what the biologists want to do, they want to somehow force these micropores to develop into plants. So to really contribute to the development of the tissue. So what happens here? So you should imagine that the background here, this black background here, or the green or the pink one, it's full with nutrients, some nutrient, and the nutrient is diffusing. These microspores are typically moving slightly, and they can capture inside some nutrients, and then they release it in some sort of switching on-off mechanism. You capture something, and then you lose it, and then you can again, and so on. So this is what they expect that happens in these plants. The point is, in a real tissue, you don't really see what happens there. So this is what they could see at the level of the petri dish. So now the problem from Leiden I've got is this one. It's on this picture I have no copyright, but on this one I really hold the copyright. So so look to this picture A. So this black box, it's in fact the plant from the Leiden biolab. What they have here, this is homogeneous Neumann, so boundary condition on the sides. They have an input flux and an output flux. They measure the flux of nutrients. They plug into this tissue, and they measure how much it gets out. You would expect the nutrients just go by diffusion. You would expect a macroscopic diffusion of nutrients in that box. But apparently, what they measure something faster than diffusion. They don't know it's really a drift inside, or it's some sort of super diffusion mechanism, and they would like to find out what could be the reason of this faster than diffusion motion. Okay, so then if you want to understand that, this is actually the moment when you need eventually mathematicians to to come up with some games. And this is the BCD, are some games we are planning to play. So these, I call them vesicles. If you think back of these microspores, you could imagine one of these microspores as being one of such vesicle. So imagine that inside you have some reaction diffusion process, and outside you have a simple diffusion process of the nutrient. Okay, and then we lied with Sander. We look in 2015 into such vesicle, and then we wanted to see, okay, it's really hard to trace them, how they move. Let's reduce them to a point in a rigorous way. And then under suitable assumption, we could show that there is a way to approximate this Dirac and the weight of the Dirac depending on the reaction fusion process inside this vesicle. But our technique really failed. It worked in an open domain, but it really failed if you want to look into bounded domain and have more vesicles, even if they are stationary. Our techniques were essentially based on green function estimates. So they are really hard to be available into more complex geometries. So what I would like to tell today, in fact, is about the picture D at the end of my talk, where you see here some sort of dual scale structure. This black box, this square, this rectangle here is the so-called macro domain. And in each of these points, I will allow myself to zoom in into the microstructure. And then these micro vesicles, these vesicles will appear at a secondary, at a lower scale into the system. So the coupling will be a bit weaker than in the pictures B and C. And this is a truly multi-scale problem. Now, it turns out that all of these pictures B, C, D can be framed into into a unified, say, formalism. And I'm going to present you very briefly what formalism I have in mind. All of this is based on constructions prepared by Sander earlier into a more abstract setting. Okay, so let's imagine for a moment that I'm looking to problem B. Forget about the rest. I have a box, a rectangle, and I have some kind of a ball or say disk-like inclusions inside. So let me denote by S the domain from where I take out these inclusions, omega I. And denote, as notation, it's say S naught would be the interior of the set. So let me define, without being very specific, a diffusion of nutrients. This would be U, the nutrient in the domain. F of U would be some reaction term, some right-hand side, and J would be the Neumann flux. F is seen like some sort of superposition operator. I will comment on what assumptions on F and J later on when this will be needed. So now, what do I do with this problem? So let me define the so-called Markov semigroup for this problem. So I'm looking, in fact, to a problem with homogeneous right-hand side, so no production and a zero boundary condition, so an homogeneous Neumann boundary. And I would like to define this semigroup, the solution semigroup, which I denote by P index T capital D. D comes from this diffusion matrix, which can have as initial data some sort of signed radon measure, mu naught. Now, as it's convenient to start with a probabilistic interpretation of another semigroup. So fix a point X in the space, and then we associate to this point some diffusion process X index T and upper index that point X in S naught with reflections from the boundary. So just it fits to the boundary condition, such that with probability 1 that this process will visit at point X. Okay, then one can show that this semigroup satisfies the PDE. So this is, in a way, you could say it's a probabilistic interpretation of this equation. Okay, but this semigroup, it's a semigroup of bounded positive linear operator on bounded measurable functions, and it's equipped with a standard supremum norm. Of course, it's a mapping from the space of continuous bounded functions to itself. Now let's extend this semigroup UTD to the PTD. This is what I would like to do now. So the semigroup extends to continuous linear operators on some LP with respect to the measure lambda, which is you should see this measure lambda as a restriction of the Borel-Lebesgue measure to our space domain, say S naught. Okay, and not only to LP but also to some kind of Sobolev functions if we want. The mapping T to this UTD applied to F is continuous from 0 in fact from the time interval into the Sobolev space for any function f in the sublet space WKP with p in fact less than infinity. This semigroup is strongly continuous, and via Rademacher theorem, you could also see it as say strongly continuous on W1 infinity. Okay, where I'm approaching to the final construction. Yes, of course, we have this property of the semigroup. So if P is not infinity, we have this nice duality pairing. But now if I'm looking to the dual semigroup, which would fit here, defined on the dual space of boundary Lipschitz function, this one is not strongly continuous. But it is strongly continuous if I'm looking it on some smaller space. For instance, I'm not going to read this notation. Is that space such that it makes this right-hand side finite? So this space here. Okay, good. Another aspect for, finite sign Borel measures on our space domain can be identified with these elements of this W minus 1 infinity in the standard way, like this. And the good thing is that now, of course, that in this ugly space, which I mentioned here, there are some LP spaces hidden there, right? So this is the construction. Okay, another little thing, L1 functions are dense in this space of measurable functions in this topology of the dual boundary Lipschitz function topology. And in that case, this semigroup, the dual semigroup of UTD, is strongly continuous from the closure of the space into this dual space. Now, the restriction, so we denote by PTD, the restriction of this dual semigroup to precisely this closure. This will be called diffusion semigroup on measures, fitting to the equations I wrote you before. Now, okay. If you have this semigroup, one could think of defining a concept of mild solution. So if you take an X in this space of where we define our semigroup, we will call mild solution. You could see this X some sort of boundary Lipschitz function. Then what it is, so mild solution would be a continuous map from 0t to x such that this variation of constants formula holds. Okay, so later on, any existence proof we may want to give of this mild solution would boil down to, in fact, to the verification of Bochner integrability of all these integrants. Okay, now this is the concept of solution, and then you could see that important thing to note here, that you see this was the right-hand side of the reaction diffusion problem, and this was the Neumann boundary condition, the non-homogeneous part. So you see that it has a nice structure as it enters there. Okay. Now, if there is some assumption on F, for instance, like this generalized Carathéodory condition, then if this is satisfied, then there is a unique mild solution. This is a result obtained by Sander Hille earlier, and in the context of when the equation itself was chemotaxis, was not this linear diffusion. So it holds for even more complex equations if they have sufficient structure. So this is basically one condition which is needed for the existence of mild solution in this boundary Lipschitz framework. Now, for the microspores situation, this is the case D I was showing you. So this is the black box, so where the diffusion of nutrients takes place. And in each point in space, I was telling that, okay, we can zoom in some balls. right? Different, say, n balls and different microstructures. And the boundary of this microstructure, this is important. So part of the boundary is of Robin type, which this is that part which communicates with the, this is the macro scale. And then the rest of the micro boundaries are homogeneous Neumann. Later on, we will see that the operators here will use the variable x for the macro scale, and the differential operators here will refer to a variable y for the micro scale. Now, in each of these points, you could zoom in geometries of seemingly different shape. They don't have to have the same shape. In the calculation, in the numerical example, which I will provide you later on, all this will be disks, but they don't have to be disks. Okay. Okay, I discussed about this sort of mild solution, but where we are with this mild solution, we are in a space like in a non-reflexive space, so it's very difficult to compute them numerically or to do anything with them, at least with finite element methods, say. So what it will turn out, I'm sorry, let me say here. Where was it? No, okay, so it's convenient to have some sort of weak solution. Well, I'm not, so what is our problem? So what is this before the weak solution? What is this exactly this problem? So this is this. So find a vector of concentration. This is nutrient. And V1, Vn would be the nutrient which enters into these micropores, microspores or microstructures. And there is something else. There is some host chemical. And this host chemical is supposed to interact with the entering nutrient and to deliver to the macro scale a signal. And then the signal is supposed to travel by diffusion further on. Now, you could imagine here that if you want that something visible comes to the micro scale, you should have some sort of switching on-off system. You could imagine some sort of hysteresis mechanism that you really do something violently at the macro scale, which if you want to see it. We decided to model such a relay system by using a bistability here. So we will take later on a chemical reaction system, which allows for a bistable behavior, hoping that the numerical solution will choose itself in which fixed point will like to go or not. So, okay, so this is the macronutrient. So you have a diffusion of a nutrient of food, say, and you see the Diracs there. You have n Diracs in the domain. So Dirac 1, 2, and 3, and n, sorry. So in each Dirac, you zoom in, and there is a coupling via surface here, this surface. This coupling via each of the ball has a coupling via surface, and there is a flux coming from the ball into the macro domain, and vice versa. So this is the coupling with the microscopic system, and this is the micro system here. So it's a partly dissipative. So it's you see here the diffusion operator is with a variable y. I should have put here a y as well, and an ODE. Now this is one way, and then there is another connection. This flux is described in a certain way, and this is the way it couples with the micronutrient with the macronutrient. One would have to make some assumptions on these functions, such that it makes sense physically, but also mathematically can be treated. I will come to that. So this is a type of problems I have in mind, and our statement is that it fits exactly as in the framework I was presenting before. We'll be able to construct a Markov semigroup for this particular system, diffusion problem with Neumann boundary conditions. But before formulating it, I need to say what kind of nonlinearities I would like to have here and there, and what do I want for when the micronutrient talks to the macronutrient. Okay, the nonlinearity in reaction diffusion systems are a sort of standard assumptions. So there are some growth of the nonlinearity. This second condition, it's a trick basically which tells this, that if you multiply with a suitable selection of of positive real number these equations and you add them up, you basically get a negative right-hand side for the sum, which allows you to control in the microstructures to have always an L1 bound guaranteed. Right, so it's not conservation of mass, but the mass cannot grow at all. And then to keep things easy, I took this condition here for the reaction rate, which basically tells that here, if one of the reactants takes a negative value, then the whole reaction term, whole reaction rate becomes 0. An alternative to this choice would be the so-called quasi-positivity of the right-hand sides. But we have chosen for some technical reason this positive cut. The connection between micro and macro, that function here, basically here, which tells the microflux is prescribed in terms of the combination between macro and micro nutrients. We took it as a linear combination. Some people in physics or say chemical engineering would call this Henry law or Raoult type law. So it's a linear term. Now about the system, which I told you before, in each of these pockets, you have to have some kind of mechanism which mimics a relay system. Well, trusting this guy Wilhelm, this is what we have in each of these pockets, and this big system can be reduced to, in fact, two equations only. And I don't want to enter into detail now. Later on, they will play a role. Important is that this system has exactly 3 fixed points: 2 stable, 1 unstable. Not for any not for any parameter, but for a suitable selection of parameters. Okay, now mild solution to this 2-hour problem. We can formulate old problem like a diffusion problem with some right-hand side, and it can be collapsed into such a matrix form. And finally, we have some sort of, a mild solution to our problem if our J's and F have sufficiently nice properties. Now, with this mild solution, so the mild solution exists. The problem is, one problem is, since we don't know that the perturbation is positive, we don't know how to prove the positivity of the mild solution at the level of semigroup. So then we think it would be good to check whether we have weak solutions to this problem. And it turns out that, yes, we do have weak solution. It turns out that this object satisfies in a distributional way the PDEs. This is basically due to the fact that both the semigroup and the integration by the diffusion semigroup and the integration by time have a regularizing property. So mild solution, not only that they are unique, sorry, there are also weak solutions. And if you have suitable assumption on data and on data, say it's positivity and L2, you can prove the solutions are positive by standard methods, and they are essentially bounded. I don't want to go into the proof of these things. I only want to show you how the weak solution would look like for the problem. So the problem was here. Let me go here. Sorry for jumping between the. So this is a 2-scale problem. So the way to do it, you test you take a test function for the domain omega and another one for another 2 for these domains. And here we also sum up over all these balls or all these microstructures. Right. So this is it's convenient to take the sums over all these microstructures. Okay, and if you do that, then the weak solution have this form. So for you have this standard parabolic regularity, nothing special. it couples with the microsystem via some flux terms, and you see this term here. You also recognize it in the one of the equations for V, which basically tells also that if this test function phi and psi coincide on this surface gamma, if I add up the two equations, the two sets of equations, this one and for U, this right-hand side cancels. In modeling terms, this means that each time the information crosses micro to macro, or vice versa, macro to micro, there is not loss of mass. So it's mass conserving. So it looks like to be it has a good structure. Okay. Now, one little comment about this microscopic objects. This V, it's a function of time and Y, but also depends on the parameter Xi. Now, since I'm only looking in endpoints, we have some freedom of what to assume on how this V depends on this parameter X. Well, we need to have some kind of measurability condition, but you can take also some more things there if you want. Okay, so we have so now we have weak solution, we have positive unbounded, we can even compute them, and I can show you how would such a simulation look like. So now these are my microspores. So I have a periodic arrangement of such balls. In each of these balls, I have this V and W system, and I have this U equation going around. And on parts of the boundary, I have these transmissions between the macro and micro. But this, once more, this should be seen at the micro scale. They're not at the same level of with the domain. But it's just for visualizational purposes. Now we see some sort of change in color, right? This is time. This is one time slice, and this is another time slice. So if you look at the color inside this microspore, so there is a slight change in color. And this is exactly this change in color. It's what the biologists would like to control. So what they would like to have, they would like to have a color equation. So to collapse the whole modeling of system of all I did into a single, say, function, or say, let's maximum one differential equation, which would model the change in color. It doesn't have to be a front, right? But that's what they would like to have. Maybe a moving front, or having some sort of indicator which shows you which cells, which pores are activated and which not, so they can follow the signal. So one would like to have such color equation. Now, for our system is fully coupled. It makes no sense. We cannot really get it. But we could ask ourselves: can we estimate how much nutrient can be stored in these microspores? Can we find that quantity, or can we estimate that quantity? That would be this quantity. So this would be the mass of nutrient in each of these pores. Well, we could, but let's look first at this microscopic system. If we forget about the diffusion, it has some quadratic terms, which in a certain limit, say in this case, K2 go to infinity. If K2 would go to infinity, this system would decouple, and then I may think of getting a closed equation for the amount which could be stored here. Now, just a thought exercise, if K2 goes to infinity, we expect to prove that then this W goes to 0. And if K2 goes to infinity, this would make this product, this term, go away from there. Of course, one has to have suitable bounds for this to happen. So this is the hope. Can we do a fast intermediate asymptotics for this sort of problem? The answer is yes, one can do that. So now that parameter which exploding, I call it kappa, the Greek kappa. And now this Greek kappa would be the parameter exploding in this equation. And yes, you can do this K to infinity and obtain such a system. Well, where of course you see the W decouples completely, and one can think, hey, if I could integrate this equation on this y of x, I could get an equation for the color, this information, how much I can store in each of these pockets. But it's not that easy because the equation is still coupled with this one. So the equation does not decouple so easily. And in fact, it shouldn't decouple so easily. So if you do that exercise, you realize that the structure is something like that. This is a nice term, which really looks to this time derivative of the color. This is this term. I should be okay. This already is a difficulty because this acts on the boundary and not on the volume. And this should be here, in fact, because the color is changing because of the input from the macro scale. So this, in fact, a term like this could stay. So this is the maximum we can identify from this color. We can identify these two terms, while this one is, in fact, still free. Okay, but one can exploit it, and one can get equations for this such a conserved quantity, and still play further to see what sort of information can we get in this right-hand side. Other effects which can change the color. Once more, the biologists only want to have this. If they have something like this with suitable information on the K1 hat and K2 hat and initial data for these sorts of colors, they are very happy. They wouldn't like to see the my slides before. So, okay, yes. Now I would like to come to a close, to a finish with my talk with the following bullet points. So we believe that there is a way to put boundary condition to measure valid equation as perturbation of semigroups. Not for any equation, but for some classes of equations. If we have access to this weak solution, then this two-scale reaction diffuser system admits some interesting special limits, singular limits, if you want, which can be explored. Some of them we did explore. We are not so sure that we have taken the right combination of k go to infinity or to 0. Maybe there are smarter choices. The B-stability in the ODE, we still don't have proof, how to say, mathematically, that the B-stability is able to change in a non-monotonic, interesting way the colors of the macroscopic scale. But we hope to get more insight into this by using numerical methods on this periodic Petri dish. Another interesting thing would be to replace the ODE system here with some the whole ODE system, the ODE PD system with some stochastic dynamics. So in each of the pocket to have some stochastic dynamics, and then to rethink the whole methodology. Can I still prove it, put it in a framework of some kind sort of mild solution? Can I approximate it? Can I have a weak solution? Can I touch them numerically? And so on. Need of course, in this, if you do this sort of two-scale problem and you want to be stability and signaling pathways crossing the macroscopic domain, it looks like that if you want to do nice things, you really need smart ways to visualize what you do. And we are far away from understanding that. And I have another bullet here saying mathematics of sensors, because my picture for which I have the copyright here, where was it? Here, you could see here that these are sensors really which collect information. The only thing which I'm insisting is that if you know how the sensor works, you have a better idea you have a better, say, chance to interpret what you see. So basically, this is the sensor location. This would be how the sensor works. This the accompanying reaction diffuser system. And of course, I did my game on reaction diffusion systems, but possibly other types of PDEs would fit into this concept. Just that for the nutrients problem, diffusion is the main mechanism which needs to be taken into account. Other suggestions is more or less a question sent to you, because there is there is much more to do. And the question is what to do from the many things to do, which are left to do. Oops, sorry. Yes, I'm stopping here. I have more things to show, but I don't want to. I will show you only if you provoke me with some specific question.
Yeah, thank you very much, Adrian, for this interesting talk. Sharka, are you there? I mean, there is probably some problem with the connection. So the talk is now open for discussion.